Okay, good afternoon, everyone, and welcome to the last GReTA seminar before the Christmas. Oh, sorry, not Christmas, before the summer break. Getting ahead of myself. To get into the spirit of things, I brought a hat. You see, it's summer, but I will take that off in a moment because it's too warm. So it's a pleasure to have Dániel Varró here. So he's a long time friend and colleague in the graph rewriting community. He has been working in Budapest for a long time on a tool called Viatra with a T, not a G, to avoid any doubt. That was one of the sort of more substantial graph transformation tools at the time, graph and model transformation tools at the time, which actually had some sort of industrial strengths tooling behind it. He moved to Canada in the meantime, where he worked for a while, and now he's in Sweden, as we just heard, or just moved to Sweden. And all of this time, he's basically working in sort of the interface of software engineering, graph transformation, and model transformation. And as I said, heavily involved in developing tools and also using those tools in industrial contexts. And today is talking about generation of graph models, and specifically domain-specific graph models. And in my announcement, at least in one I sent earlier on one of the mailing lists, I said that in a way this is a bit like a sub-solver for graph rewriting or graph-based models. So we'll see whether that is true, and whether there is any deeper sort of relevance to this. So yeah, Dániel, take it away, please.
Thanks a lot, Raiko. It's my really great pleasure to be here, and I give a talk about what we have been doing related to graph model generation. But before I get to the core topic, I will give a bit of a background of where we were kind of coming from some time ago, and this also provides us a technical foundation of the techniques that we are using afterwards for graph generation. In that regard, for a while we have been working on some foundations, query-based foundations of domain-specific graph models. First, the Viatra as a model transformation tool, and then inquiry as a graph query engine. And some of the motivation of that work takes back to as early as 2009, sometimes even before. Specifically in 2009, we have been working together with an automotive tool provider, which was developing a modeling tool, domain-specific modeling tool for AUTOSAR. AUTOSAR is a standardized software or software-hardware architecture heavily used in the automotive industry. And this is supported by quite a couple of modern modeling tools. And the standard itself also contains quite a set of design rules, you could call also well-formless constraints, which need to be respected by each valid car architecture. And then if it's violated, then the engineers, the systems engineers, need to be notified immediately. And there, the challenge was that AUTOSAR defines some 500 of such design rules. And some of the AUTOSAR models, while they are typed and attributed graph models, they may have over 1 million elements. And those models are constantly evolving by the designers. So this was one technical challenge when we decided to fork our graph incremental model transformation technology into graph-based queries. So technically, in this talk, I will talk about the generation of domain-specific graph models. I assume that those graph models, the structure of those graph models are defined by, I will call it a meta model. You can also take this as a type graph. We will be working with typed and attributed graphs essentially. For instance, in case of a railway domain, the track elements may have switches or may have other segments. and then signals can be assigned to some track elements. That's like what the meta model would capture. And then further constraints of the domain can be captured by graph patterns or graph queries. Formally, we will be using a fragment of graph predicates which converges to first order logic, as we know for a long time along various results in the graph transformation community. Anyhow, in this context, these graph queries will be capturing violations of constraints. So if you know the constraint language of OCL, object constraint language, then it captures the positive situation, what needs to be maintained. When we are using graph queries for capturing the validformness rules of a domain, we always formulate the cases which are the violating cases. So when we match the constraints or the queries along the instance graphs or instance models, then the ideal situation is that there are no matches of the graph patterns, and then each match of the graph patterns indicates a violation of the constraint. So once the designers update the models, we hope that eventually those matches would disappear from the design. Why is this important? Also, practically, we actually do graph pattern matching for this high-level graph query language. Conceptually, you have as if like a left-hand side graph of a graph transformation rule, which you wish to find in a host graph. For instance, one constraint would capture that all sensors with a switch that belongs to a route must directly be linked to the same route. And then during the matching, you wish to find a match of each node. You can call them like variables of your problem, in a way that the constraints which constitute the edges of the pattern graph are also respected in a type compliant way. So these are practically what I would consider domain specifications for graph generation. And in the Viatra approach or inquiry approach, our core idea was to, since in a real engineering design, engineers try to keep their systems consistent in most of the time. For instance, you don't commit a piece of source code into GitHub if there are compiler errors in the source code. So similarly, the number of violations at any point in time are reasonably small, ideally 0. So we can cache the results of the graph patterns that constitute the constraints. This way, we might use more space, but since by caching the matches of those graph patterns, we can instantly retrieve those matches when needed. And then when the design changes, we update those caches upon each model change. We have based our approach on the GReTA based techniques, which are dating back, I think, to the 1980s with some modifications, and that constitutes the core of the Viatra framework. The Viatra framework is still there. I think the only key difference is that in the last 5 or 6 years, this has dominantly been maintained at Inquiry Labs, which is a Hungary-based, now it's not only Hungarian company, which continued working on the industrial exploitation of these technologies. Now, but this talk is dominantly about generating domain-specific graph models, and why are we doing so? Why are we interested in that? And I could give a couple of a couple of motivations for this, because we ended up in similar sort of challenges from multiple different practical perspectives. The first one is related to safety critical systems, especially avionics, where safety standards mandates that you cannot just trust the outcomes, the outputs of tools, or like design or verification tools that are used in engineering such systems. And software tool qualification is a process prescribed by those safety standards that, for instance, necessitate very detailed and very thorough testing or other verification validation activities for the tools themselves that are used for designing aircrafts. So when you design an aircraft, this means that companies often use like 40, 60, 80 different tools. And unless a tool is qualified, then you have to recheck the output of the tool. And generating test cases for the tools themselves, that was one motivation. Another motivation is related to the assurance of like critical autonomous systems, such as autonomous vehicles, self-driving cars, and the like, especially coming up with challenging situations. I will get back to this later part of the talk. And interestingly, there are other communities which have been working on graph model generation. One community to mention is network science, to study different kind of distributed and decentralized systems. They use synthetic graph generators in the context of many simulations. And if you go to the graph database community, they also heavily rely on benchmarks. One of their challenges that how to assure or how to guarantee that graph algorithms behave like consistently and efficiently on real data when you cannot get access to the real data, since it often has IP or restrictions on the intellectual property. So companies cannot show you the real database, yet you need to demonstrate that your, I don't know, graph query technique would scale well, would work well in the context of the real data as well. So these are like 4 different cases that brings to the same conceptual challenge. Imagine that you have your domain specification given in the form of like a meta model or a type graph and a set of well-formless constraints. In this running example, I will be using a meta model of a state, or like a simplified meta model of state charts, where we have transitions and an abstract vertex node, which is either an entry state or a regular state. And now we have well-formless constraints capturing, for instance, that the entry node shouldn't have more than a single outgoing transition. We shouldn't lead an edge to the entry node of a state chart. And it's also not a valid state machine if the entry node doesn't have an outgoing transition. So that's like the three simple constraints. And now the graph model generation, consistent graph model generation challenge consists in deriving instances of this meta model, which satisfy all the well-formless constraints. And one way of doing this, and there are many researchers who have attempted this and who have did this, is that you take the model generation challenge, you translate this into an equivalent logic-based formalization, and then you use backend logic solvers like, I don't know, Alloy, SAT solvers, CSP solvers, SMT solvers, and you use those solvers as a background or like as a solver to derive instances of graph models. And yes, this is conceptually fine and very appealing, but there is one practical problem, which is related to scalability. typically, I think the largest graph model that we have ever been able to generate with this sort of approach after many different tricks of optimization still didn't have 100, or like may had like 100 graph nodes. And I will come back to this point later on, what's the setup. But related to this graph generation challenge, we started a longer term agenda, which we eventually started calling a core disk, related to or for providing automated graph generation techniques, which would satisfy 4 core properties of graph generation. One is consistency. So consistency related to that, like all well-formedness constraints are satisfied. And ideally, a related property along this would mean completeness, that in principle, one could generate all consistent models of a particular domain that satisfy the constraints. Another property is related to the realistic nature of models. And in this case, the particular aspect of realistic nature is related to that we have been investigating is related to the graph structure itself. So imagine that you receive a graph model containing real attributes, and now you wish to derive a syntactic one, which cannot be distinguished from a real graph model after you remove all the sensitive data. You remove all the attributes, you remove all the parameters, and after this, we would like to see that the actual structure of the two models are very close to each other. That's one aspect of realistic nature. Another one is, of course, like having models from a realistic distribution. Item number 3, or property number 3, is related to diversity. And diversity in a model generation context can mean, I think, at least 2 different things. One is that each single graph that we generate shows a structural diversity in itself. So it uses model elements or different kinds of model elements. And another aspect of diversity, which is important, I think, from a testing perspective, is that if we take any pair of graph models that we generate, there should be like a sufficiently large distance between them, no matter how we measure the distance. And finally, the 4th aspect is related to scalability, which can mean that the size of the graphs grow or the number of the graphs grow. And when we generate new and new graphs, it still takes roughly the same number of time as before. I see a question, and I'm at a section point, so I think I would stop here and get that left's question.
Okay, just on the issue of size you were talking about. So how do you control the size of the models that are generated? Because in principle, they're unbounded, I guess, or does the meta model already restrict the size? Or is it that the user says, I want models up to a certain size?
It's dominantly the final option, that the user can put further constraints on the size of the designated size of the model. And then these constraints will be incorporated as part of the generation process, as we call it scope kind of constraints. So we take the domain specification as is, we don't change this, but we can get further hints for restrictions or constraints on what are the kinds of graphs or what are the size of the graphs that we would like to derive.
I would have actually one more question, if I may. I don't know. So it's on the constraints. So if my domain of interest, so to speak, happens to be not specifiable in first order logic, will it still generate me a model which then, okay, has some properties possibly which I don't want, but it does satisfy all those specified constraints nevertheless? Or so, I mean, you gave the example with the what was it, state machines, I think, or something. So if I happen to be interested, so let's say I want to specify my graphs have to be connected. which cannot be specified in first order logic. I don't know if you can do it. So what would happen? Or can I do it also as a limitation of the approach? Let me ask it like that.
Okay. Like connectedness is actually incorporated as a kind of like quality attribute or like objective in the search. So we try to come up with graphs which are connected. But if you would select another property which is not specifiable in first order logic, with the first order logic with transitive closure to be very precise, then of course we wouldn't be able to assure this. We could assure everything else, but not that.
Okay, thank you.
Okay, so I think then I go to next question. So consistency is one aspect that I think I will spend some time on this. But before that, let me give you some insights about the other two properties, where we found that there is not that much amount of work, which is the realistic and diverse nature of graph models. And especially in the days of when machine learning approaches are becoming that popular, we hear often that, you need to take your samples from like a realistic distribution. So what is actually, there comes a difference of, is there any difference between like diverse and realistic graph models? And one of the messages that I would like to convey here is that, yes, I think diversity and the realistic nature of like graph models, domain-specific graph models, can be actually very different. And I would like to highlight or give you like 3 groups of examples of state machines. All of them are like regular instances of state machines. And if we check the ones that are in the top left corner, you can easily imagine a system which is consists of a single state and like a loop transition there, then like some initial state and then a loop transition, or like 2 initial states and the loop transition. All of this looks like that we are modeling some realistic systems. But if you compare like the group of these graph models, all of them look alike. Yes, there are a couple of initial states, and then there's a looping transition, and then what's happening there. If you go to this other group of state machines, you see that there is much larger structural diversity within and also between the models. So I would say that diversity is great here, but if you think about the semantic meaning or like of the various state machines, you would say that, okay, I mean, none of them would probably represent the real system. You would call some of the cases as borderline inconsistent, where some of the constraints might even be violated. So when we generate models, we ideally wish to derive models which are both realistic, so they could represent like a real system, and they are also structurally diverse. And on that note, you can also consider various kinds of realistic metrics, and realistic graph metrics, you find quite a few, or you can borrow quite a few from the network science community. And it starts like very simple ones, like the out degree, which is like number of neighbors of a node along an outgoing edge. They call it node activity, which is the number of edge types in which node O has at least one edge. And then there are some more kind of complex ones, dimensional degree, which is the number of neighbors along a set of edges R. And these are like the graph metrics that are quite actively used by the network science community. However, when we were investigating some real models, real graph models from a software and systems engineering context, we have found that there is actually a metric which is not that much considered in network science, but it's actually respected by all real models in like engineering, which is that the number of constraint violations, the number of violations of well-formed constraints are very few in real engineering models. Imagine, which means that in order to address the in order to generate realistic models, we also need to be able to generate consistent ones. Otherwise, we can end up with graphs which, like with a fully random generation, you can end up with, you can follow many metrics of traditional metrics of realisticness, but if you randomly generate a graph, you will violate those well-formed constraints. So altogether, realisticness and consistency, it's not totally independent from each other. We need to, real models are dominantly consistent. This was one empirical finding that we had. So, and this is also one motivation why we ended up investing a lot in consistency. Another one is like diversity. And for diversity, again, we looked back to what graph-based abstractions can provide. And we interpreted neighborhood abstractions, neighborhood shapes, Arendt Rensing's earlier works, and we turned them into diversity metrics. So what are those neighborhood shapes? Imagine that you have this instance models. I will give a not so precise interpretation just to get you the idea. If you consider a neighborhood range of 0, then practically the types or in the shape practically correspond to the classes in your meta model. Now, if you consider the types plus the relations of the meta model of M1, then practically we have something that's very close conceptually to what meta models would describe. And when you talk about meta model coverage as a testing criteria used in many model transformation and testing papers, that's practically the same setting. However, we can further divide classes based upon the neighborhood, of different kinds of nodes. So for instance, we can distinguish between transitions which lead out of the entry state or which lead out from non-entry state. It's like conceptually close to that. We derive subclasses of the class transition, which is defined in the meta model. And we derive these subclasses based upon some sort of queries. So this initial transition class can be defined that there is a source edge that leads into an entry state, and this predicate needs to hold. And then for the intermediate transitions, this predicate is actually false. Why is this like a neighborhood of range 1? Because we only considered single hops from the particular object or node of interest. But gradually we can extend these neighborhoods. We can say that for a neighborhood of 2, we can further distinguish between initial states and like intermediate states with appropriate queries. Anyhow, based on traditional neighborhood shapes, we established a couple of diversity metrics that we can use afterwards for as objectives when generating graphs. One of this is related to external diversity. External diversity is practically related to a pair of models, and we would like to, and this external diversity is related to how many different shapes are there in the intersection practically or in the disjoint union of the two models. So how many shapes are only covered in one model but not the other model. For internal diversity, we measure how diverse a single model is in itself. So we practically calculate the number of shapes and divide this with the size of the model in a certain sense. And then we wish to derive a suite or like a set of graph models in a way that we are maximizing one or other diversity metric. That's, I think, the high-level idea related to diversity and the realistic nature of models. And then, as the next stage, I would like to get to the challenge of generating consistent graphs. And as I mentioned, conceptually, this is very straightforward. You can represent graphs as predicates by introducing a large number of variables. For instance, you can say that you introduce one Boolean variable for each object and the type. So like for transitions, vertices, entries, and states. You can introduce a Boolean variable for each pair of objects for each reference type. But then the problem is that if you have a graph with like 100 nodes, then we already introduced a set solving challenge with 20,000 Boolean variables, which one could say it still should be within reach of some of the solvers. But then we get to the constraints, because now if we have a language level constraint that captures that between that there should be no incoming transitions to an entry state, and I wish to unfold this constraint over this Boolean model, then I end up with over like 30,000 atomic expressions for the formulae that I would like to check. And this part for like a model of like 100 objects, and this part is not very appreciated by set solvers. And we ended up finding that model generators that are directly based on logic solvers somehow fail to scale. And then that was a starting point when we decided that, okay, instead of mapping the problem to mapping the graph generation problem to logic, let's try to lift the concepts of set solving directly over abstract graph models. So what are those techniques? Essentially, we have borrowed or lifted techniques from very traditional set solving like DPLL algorithm, which stands for Davis, Putnam, Logeman, and Loveland. This technique has been developed for set solving of clauses in a conjunctive normal form. So this is the formula, and we would like to find an evaluation or mapping of the Boolean variables to the appropriate truth values so that the formula is evaluated to true. And during set solving, we are refining partial variable bindings. So for instance, we already made a decision about that variable A is true. And now the algorithm operates in a way that it makes a decision about, selects a variable and makes a decision. For instance, variable C is either refined to 0 or refined to 1. And then once we make a decision, this is done by decision rules, we also apply unit propagation rules to propagate the consequences of those decisions. So for instance, if I decide upon that C needs to be 1 or C is 1, then one consequence is that D has to be 1, because otherwise I think this cause would never hold. In that regard, the SAT solving algorithm is a repeated execution of such decision rules and unit propagation rules. Now, how do we, basically our approach for graph generation, consistent graph generation, is lifting these principles on the level of abstract graphs, which consists of a couple of key ideas. And again, I will only highlight the key ideas. First thing is that we are operating on the level of partial or three-valued graph models. A three-valued graph model looks like a regular one, but it's extended in a way that uncertainty in the model is explicitly represented. So in this example, we already know that the state machine has an entry state and the transition is linked, is coming out of the entry state. This is certain information, but we don't yet know where this particular transition is leading to. Maybe it's leading to the entry state in itself. Maybe it's leading to a new graph node, which is again uncertain. So we do have uncertainty with the existence or non-existence of edges and nodes. Now, during the graph generation part, we are applying the equivalence of decision rules and unit propagation rules. In case of a decision rule, we reduce uncertainty. This can be that we are splitting uncertain nodes. So for instance, this previously uncertain new node is now split into two. It still remains the uncertain kind of generator node. And then we introduce a new state, which is solid line. So this is now a certain state, but we still don't know, for instance, whether this transition leads to the entry state or to this new state. Another way is that we are refining uncertainty of edges by refining this abstract or partial graph model. Now we made a decision in this case that the previously uncertain target edge between transition and entry is the real one, and as such, this no longer exists. So now in the refined version, I know that there's a transition from the entry state to the entry state, and there is no target transition from the transition to this new generator state. The third idea is that we need to be constantly monitoring and evaluating the well-formed constraints. We cannot wait until the very end. So one could think about like a naive model generation approach, which randomly generates a large number of models and then checks the constraints one by one on each instance. Unfortunately, if the constraints are getting more and more complex and less local, these constraints will be violated by practically a probability of 1 in case of random generation. So we need to do something with a query evaluation, but since we are not working with regular instance models, therefore we approximate the results of query evaluation in two ways: by calculating the so-called may matches and the must matches of queries, which practically means that if we find a match of a graph pattern in a partial model, note that this model still contains uncertain elements. So it's not yet an instance model. It's still like a partial graph model with uncertainty, but there is a certain match of that graph pattern in the actual abstract model. Then we know that the refinement calculus ensures that this well-formed constraint will be violated in all refinements of this abstract model. So if it's violated once, if it's surely violated once, we cannot get rid of the violation. So there is a certain level or a certain level of monotonicity in how the graphs are generated, even though the underlying constraints still contain negation and other kind of complex first order logic constructs. And then the fourth idea is related to state encoding, which means that we need to check during the exploration whether a certain state, which is again like an abstract graph, has been already investigated or not. And this brings in principle to like graph isomorphism related things, which can be detected, but if the state space is large, normally this is approximated. Traditionally, like in some solvers, like in Alloy, they introduce symmetry breaking predicates, which have the property that if you find that the predicates are the same or evaluate to the same value for two models, then you know that the two models are isomorphic. We actually do the other way around. We do calculate the shapes of two models, which means that if the two models are isomorphic, then we know that their shapes are identical. But we use practically this in the other way around. So if the two shapes are different, then we know that the two models cannot be identical. As such, if we don't really have to evaluate graph isomorphism, but when we can go along with such equivalence classes because we want to enforce diversity anyhow. So in that regard, graph shapes are used also a means for reducing the checks for graph isomorphism and also enforcing like diversity. Altogether, the graph generation approach or the graph solver approach has a couple of nice theoretical properties or guarantees. One trivial thing is that the derived models do satisfy the well-formness constraints. Another one is that for any finite model, there is a finite sequence of refinement operations that derives the model. Conceptually, there is a certain sort of completeness guarantee. So for any finite and consistent model, there exists a finite derivation sequence of refinement operators from the so-called most generic partial model that derives the model. And another two is any consistent partial model of size n+1 are derivable from partial models of size n. So we can continue the generation basically along the borders. And the final one is that if a constraint is surely violated along an exploration path of a model size n, then no consistent models kind of exist. And just to give like an idea why we believe that for model generation, this is interesting. SAT solvers and SMT solvers, they are very good in the rapid detection if well-formness constraints are inconsistent, so there are no models. Note that we give no such guarantee. There may be cases that we cannot detect certain inconsistencies, but when we are generating graph models, you will see that we will be actually faster. So on that note, let me give you a brief insight in some of the evaluations that we carried out. So first of all, there is already like an open source tool which has been around. We call it the Viatra solver or Viatra generator, using Eclipse-based technologies and using a couple of backend solvers integrated, also traditional ones like Alloy or Z3, and it's tied to standard EMF technology and Viatra queries as the constraint language. Now, we have been evaluating this the scalability of the solver in a couple of case studies and compared it to, in this figure, Alloy-based solutions using different kind of SAT solvers in the background. Essentially, we could generate models of 1 to 2 orders of magnitude larger. So models with I don't know, 600 and 700,000 of model elements, where the equivalent solvers fail to generate models of 100 elements or the like. So in that regard, the combination of evaluating the constraints in an incremental way, or incremental and approximated way, using graph shapes and integrating some of the best abstraction techniques or some good abstraction techniques from foundations of graph-based techniques paid off. So that's one set of measurements. Another set of measurements were related to diversity. And this is, again, another kind of unexpected issue with using set solvers or SMT solvers for model generation. In this case study, we had a large set of human models originating from some state machine-based assignments from university courses, and these violet ones represent the kind of mutation score of those real human models, how variable, how diverse they are. And what you find is that in case of logic-based solvers, the diversity of a set of models derived is much smaller than human models, while in case of the Viatra solver, the diversity of the model set, thanks to graph shapes and the other diversity metrics, is much higher than human models. So actually, when you are using these techniques as test cases, you are actually doing better than what human models would be doing. That's also highlighted in this other plot, which was measuring internal diversity of the models. This is also interesting because the diversity metrics have been correlated with actual mutation score that was used in testing. We also integrated a couple of backend solvers, so traditional backend solvers, for instance, for handling attributes or doing some sort of multiplicity reasoning using LP solvers, which also links back to Detlef's question of what to do with scopes and the like. We tried, our added value is in the structural reasoning, and when it gets back to numbers or attributes, then we try to loop back to other existing solvers where there is significant amount of body of knowledge. And now I'm getting close to the end of my talk. Let me give you one example of how this graph solver has been used in the context of design time assurance and system level test generation for critical cyber physical systems, which has been a challenge. The challenge has been around for a while. It's, I think, the first time we came across with this was in the scope of 2 European projects running in Budapest, which was concerned with the testing, system level testing of autonomous robots, in the way that the robots, so system level testing, we consider the robots as black boxes, and but we wish to generate a diverse set of test environments with various obstacles, and one test case is whether the robot can navigate it or not. And the approach that we were taking is that instead of directly setting up the precise physical coordinates, we did the so-called qualitative abstraction into an abstract graph model, and then generating a set of diverse graph models, which are then turned into concrete positions. And the same approach or conceptual approach is quite much applicable for helping the system level assurance of autonomous vehicles, where we are trying to, so in case of system level assurance, those companies are using various simulators, very sophisticated ones, which are set up in a way that different kinds of behaviors would be investigated. Let me give you one example. One of such like group of scenarios is related to lane change. A lane change scenario for an autonomous vehicle is not so dangerous if there are no cars in the other lane, but the same scenario can be much more dangerous if there is a car in the target lane, which means that if each like actor has the same behavior, the difference is only in the environment of the autonomous vehicle. So when we are describing such traffic scenes, we can again use graph models, for instance, for capturing concepts in the scenery. So scenery are like the tables, the road, the house, which are there like permanently or in a static way. We can use those graph nodes for capturing the dynamic elements or the actors, so vehicle A, vehicle B, vehicle C, and the physical distance and geometric relations between those actors can be abstracted into graph edges. So for instance, vehicle C is in front of A. So this is like one graph edge, or another edge could be that B is on the road and not on the pavement. And in the like automated synthesis for system level scenarios, we do define functional scenes as abstract, using qualitative abstractions in the form of graph models. And then these functional scenes define the respective constraints for intervals and regions. And then we designate the exact numeric values for the concrete scenes, which are then simulation ready by solving these geometric constraints. So we first aim to derive a variety of a diverse set of graph models. Then we set the constraints of the physical placement in accordance with the qualitative constraints on the graphs. And then we solve or we try to set up the actual positions of the cars on a physical level. Why do we do so? The idea here is again that if we have structurally different situations, so basically we enforce some diversity on the level of abstract graph models, then they result in semantically different scenes in the end. So we can enforce diversity, and if you just randomly try to place cars on the road, then certain constellations, rare constellations or rare cases of traffic situations are unlikely to happen. So in that case, from test generation perspective, we try to enforce diversity that way. And then as part of scene concretization, we take one graph model, and we, with the search-based techniques, we try to place the actual cars on the maps, which maps are like digital twins of real places. So in one case is a physical intersection in Budapest, another one is a test track, Zala zone, which has been built for testing autonomous vehicles. And then at the end, we use existing simulators to replay the actual scenarios that has been generated to see if there are critical or close to crash situations or the like. So this is like one application of a graph generation technology in a modern context. And finally, let me also touch upon some ongoing work. And this is carried out as part of works partly supported by an Amazon Research Award. So our ongoing work is a system called Refinery, which is aiming for graph solver as a service. As part of this, we try to get rid of Eclipse-based dependencies. So imagine you would get an editor for capturing models, constraints, and the like running in a web browser. You can specify the meta model. You can specify the well-formless constraints. You can even specify like some initial partial models that need to be included. You can define some certain scopes for the designated analysis size, and then you hit the generate button, and in the end you get some instances satisfying the actual constraints. So here, one core component that we have been working a lot is gets rid of EMF-based technology, and it would provide like a in-memory model store for partial models, which provides native support for model differencing and model merging, and then would also serve as like helping storing state spaces for design space exploration and other ways of logic reasoning. We are still using incremental graph query technologies. Now we can evaluate queries over different model versions instead of evaluating them on single models. We can do like partial model analysis for like validating well-formless constraints, but also we do tolerate inconsistencies in a way that detected inconsistencies wouldn't crash the models. You could still save the models, you could still work with the models, and they would be like interpreted semantically by for-valued logic analysis. We also integrate various kinds of logic solvers for that. And then we try to bring together a former work on design space exploration as well as the logic solver into the same framework at the end. So this is partly ongoing work. We plan like first public tutorials of the technology for the upcoming fall. And altogether, I think I'm reaching the very end of my talk. The core of the talk was related to automated graph generation of graph models, especially like consistent graph models. I've been also discussing differences between the realistic nature and the diverse nature of graphs, and how graph shapes can be used to improve the diversity of graph generation. I shared some thoughts about how our graph solver operates, which is lifting up set solving technologies on the level of partial graph models formalized in three-valued logic. In a sense, reaching quite favorable scalability results compared to mapping the whole problem down to logic solvers. And I showed you one application scenario related to the testing of autonomous vehicles. And stay tuned with respect to our ongoing work on refinery as a framework. Thanks a lot again for listening to me, and I'm around if you have further questions.
Okay, thank you very much. Yeah, very good. So I have a question which is related to the graphs with uncertainty that you presented. So the graphs with the probabilities for certain nodes, and I can't remember whether we had a probability on edges as well, but just a probability on nodes to exist or otherwise. So I mean, you have a way of matching them. Does it mean that it's also straightforward to do transformations on them?
So first of all,
regular graph transformations on graphs with uncertainty. So that would be an interesting.
I have to tell that they are not really probabilities in the sense that we use like a logic-based, so three-valued logic-based formulation, not that much probabilities. So we only have like the three values of the logic true, the logic false, and the undecided or uncertain. The transformation part is was missing from the core like Viatra solver framework, because we kept, I mean, it was hidden behind the scenes, but you could not write custom generation rules, which I know that quite a couple of researchers, I don't know, Dániel Strüber, Gabi Tenzer, and then Stefan Schaller, they are using like a customized set of generation rules. So this is something that we are aiming to add back again in Refinery. Yes, we might sacrifice some completeness claims, but it may be more practical. So that's something that we wish to offer again, to write such rules, not only the queries. The queries are there and have been there anyhow for the constraints, but not the rules for manipulation that should be coming as part of Refinery.
So conceptually, what would happen there? So if you're thinking of, let's say you have a rule that matches a node that is definitely there and a node that is possibly there, yeah, maybe with an edge between them, okay?
Mm-hmm.
And then you're creating another node, let's say.
Mm-hmm.
Yeah, so what would the status of that node be? Would it be also a node that is sort of possibly there because you don't know really of because one of the input nodes wasn't there with sort of full certainty, or what is the kind of
you can, so like the most conservative way of course, so one extreme or the most conservative approach would be that, yes, you only apply graph transformation rules on certain matches. Like when you do I don't know, abstract graph transformation, then you focus on a match, then you apply the rule there, and then you do again generalize into shapes, and then that would be, I think, one way of avoiding some kind of nasty loopholes and problems. Of course, one could also say that it's part of the rule, so the rule needs to specify what to handle, and then we can execute, but you may not end up with something consistent or which is well-founded, so that you could prescribe that, okay, if there is a potential match, I add elements for sure, or if there's a potential match, then I maybe add uncertain elements. But I get this should also be kind of possible because you may have inconsistent elements. And for instance, getting rid of inconsistent elements would be a transformation that is, in that case, manipulating elements with a specific semantics. These are, I think, two extremes how this could be handled. But if you I mean, I think if any of you have other meaningful ways of reintroducing rules in transformation rules in that context, I would be very much open to discussing this, because seemingly there is not a uniquely meaningful answer.
Yeah. I mean, there is a related theory potentially for rewriting on fuzzy graphs. It obviously is more sort of refined in a way, fuzzy graph than the graph with uncertainty, because you have sort of basically anything between the interval of 0 and 1 as a value attached to all the graphical elements. But there's probably
this could be also interesting in other lines that we have been.
No, I'm just thinking. I mean, I can't remember exactly what they do, but they must have a way of deciding essentially, if they do a rewrite step, how do they assign the values for the new nodes that they're generating.
We practically follow this kind of information, like lattices defined by information ordering and refinement in a way that try not to end up with like inconsistencies in this, what is called Belknap-Dunn logic. I think that's the equivalent, and that's, I think, the right fragment of logic that we are relying upon.
Yeah. But I think one probably needs a use case here first to understand what the rewriting on such graphs actually means, isn't it? To get an intuition of what is the right level of expressiveness of the rules and what is the effect, basically what the effect should be. Okay, interesting. Right, any other questions? Sorry.
Detlef has his hands up.
Sorry, I need to move my chat box to see everyone else. Yeah.
You're ignoring my hand, Raiko. Okay. So I think it's my turn.
I had my chat on top of your face. Sorry, on top of your face.
It's okay. Just on this business of checking the constraints, you explained, or at least I got it this way, that you have constantly to monitor the consistency because it's too late to leave it to the end and then check. So you have to do it all the time, kind of, at certain points at least. So what about, this would be kind of a radical idea, if we had a different specification language for instead of these logical constraints, namely simply graph grammars. So obviously graph grammars, that's the very idea of them, define graph classes, hence constraints. And then, generating the models would happen by the rules of the grammar. So the consistency would be automatically given. Now, I guess already what you will be saying, we can't expect engineers to write graph grammars as specifications, but let me know your thoughts.
I think the practical challenge for asking engineers to write such specifications is that, I mean, if I have like 500 constraints of AutoSAR, then in order to come up with a rule set that allows the generation of all consistent AutoSAR models, but only allows the generation of consistent models, I need to kind of consider first like the interaction between any pair of constraints and then maybe any triple of constraints and the like. So actually constructing the rule set once the number of constraints grow is a practical kind of challenge, or can be a practical challenge in that respect. So like it's probably already a challenge to capture the 500 like constraints, but those people who define the standards, they are reasonably well with this, at least specifying it textually. But I wouldn't like eliminate the idea of combining like constraints with specific generation rules, because then it could be like could be even either more efficient or like you avoid certain parts of the generation where it's very unlikely.
Of course, as always, it would be ideal if one has translators from one format into the other. So here's a set of constraints, give me the equivalent graph grammar, or other way around. But of course, it's not that easy always. So, But okay, thanks.
I was predictable. Yes.
I mean, there is in theory, there is this theorem, is it called a filter theorem or something like that?
For certain logics, it's possible, but I think it's quite restricted, isn't it?
Probably not in front of that logic.
I just had this idea, with this consistency thing. If we stick to graph grammar rules, which specify the class of interest, then it's automatic. So it was just a naive thought. Okay.
No, it's not so naive in the sense that, I mean, for handling multiplicity-related constraints, I think the community has gone quite far in deriving the respective rules. yeah, you end up with like a large set of grammar rules for growing the graphs, and they would respect I think many or most like constraints related to the multiplicity of different elements, which is like one fragment of relevant constraints. But there it's actually, I think, working very fine.
I think also one issue is if you have logic-based specification, it's very easy to have an AND, obviously, right? You just add a constraint. It's not that easy if you have a set of rules.
That's true as well.
Yeah.
That's true as well.
Okay, thanks.
Okay, any other questions? Otherwise, if there's no more question, then maybe we can close the public part of this. So let me put my hat on again and wish you all the best for the upcoming summer. And thank you very much again to Dániel and to anyone who attended this seminar, but also all the other ones that we had this academic year. And yeah, so we'll see each other again in September.
And thanks a lot for the invitation again.
Yeah, pleasure.
Yeah, and also just to say from my side, thanks a lot, Dániel. Thanks a lot to all our viewers. And just to be slightly more precise, we'll be back on September 8th with a talk by Marin Altenmüller on surface embedded graphs. So I'll just close the live stream. If anybody still wants to come over for a chat, please do join us on Zoom. The link is posted on YouTube as well.